You all know me, William. We met during the interviews. The slides are on Slack, so if you hop on cohort 3, you can download the PDF. So you're going to be hearing from me for like the next 3.5 weeks-ish. And we're going to do a deep dive into all the technical details of mostly Ethereum, some cryptography, and Bitcoin as well. Right. So yes, the next 3 weeks, roughly going to cover these things. After me, there will be a couple of guest speakers. One of them is going to go deeper into the EVM, or the Ethereum virtual machine, and another speaker is also going to talk about Hyperledger. Right, and we've talked about that like final project at the end of the term, or at the end of the course. And basically this is a project, it's a technical project that you work on throughout the bootcamp, and then at the end of the course you're presented to various recruiters and other prospective employers to demonstrate your technical knowledge and understanding of blockchain and decentralized technologies. These could either be done individually or as a group, if you guys decide to form either like pairs or work by yourself. It's a very open-ended project, so you can write a smart contract, you can contribute to an open source project, you can even try to build your own blockchain if you like, but basically anything that demonstrates your understanding and your depth of technical knowledge. There's only 5 weeks of instruction in this bootcamp. The 6th week is for you to work on your project. You can come in to 7-Gate, you can work here. I'm here most days, so I'll be around to answer questions. And also on the 6th week, where we haven't decided which day yet, but there will be mock presentations where you present your projects and we'll provide you with feedback. And then the actual presentation with all the recruiters and employers will be on the 7th week. Any questions about the final project? Right, so today and tomorrow we're going to be talking about cryptography, just to get everyone on the same page. Today we're going to be talking about pretty basic things like hash function, encryption, digital signatures, and then tomorrow we'll be going into the more meaty things. We'll talk about zero-knowledge proofs. We'll talk about Monero and Zcash, which are two of the main, I guess you would consider them like privacy-focused blockchains. So it turns out that cryptography, or when you look into history, it turns out that humans have this tendency to want to communicate in a private, secret manner. In like the pyramids, people discovered hieroglyphs that the Egyptians left, and they're basically like a superset of the language that Egyptians used to communicate. And it's extremely weird, because why would they need to communicate secretly? And looking throughout history, this just seems to be something that humans naturally need to do. So we'll be going through some pretty basic cryptography schemes. So there's this thing called the Caesar Cipher. This is like your classic kids game that you find at like the back of a cereal box. There's your plain text. Let me see if I can bring it. Right, so the Caesar Cipher contains this cipher or key, and that is like a mapping from a plain text to your ciphertext. So here we have our normal alphabet, A to Z, and then the corresponding secret cipher. So here A maps to X, B maps to Y, and the way you apply the cipher is you have your plain text. So here the quick brown fox jumps over the lazy dog, and here you look into your cipher and you encrypt your plain text into the ciphertext. So now the idea is that anyone who intercepts your ciphertext has no idea what the plain text was, and you're able to communicate secretly. The problem with this is that it's vulnerable to what's known as a cryptoanalytic attack, or a ciphertext only attack. So this exploits properties of your form of communication. So in this is an example of the English alphabet. it turns out that vowels are used very often, more specifically E. So if you can collect a lot of messages that are encrypted using the cipher, you can actually derive what the cipher is if you have enough ciphertext. So obviously that's not a really secure cipher, because now if you collect a bunch of secret messages, you can suddenly deduce what the plaintext message was. So yeah, that's the Caesar cipher. This was famously used by Julius Caesar in the Roman Empire. And it's a very early, very basic form of cryptography. Fast forward to World War II. This is the Enigma that the Germans used to encrypt their Morse code messages that they sent during war times. It's a little bit more involved compared to the Caesar cipher. You have this mechanical device that you use to encrypt your Morse code messages before actually sending them over the air. And how it works is you have this keyboard, which you type in your message, and then when you press a letter on the keyboard, well, actually, before you do this, you have to set up your Enigma. So what that consists of is a plug board. It's hidden here, but it's basically a bunch of holes that you have to combine with, or you have to connect with cables. And then you have these rotors, which further scramble the message you're trying to send. So when you enter a letter T, it goes through the plug board. It gets scrambled a little bit, and then the output goes through all the rotors, which are configured in a way that is the same on the sender as the receiver. And then a letter lights up on the light board. So right here. So the idea was that you communicate with the receiver, you set it up identically, you type in your secret message, it gives you a encrypted message, and then that's the message that you type with your little Morse code thing. And then when they receive it, they type in the encrypted message, and then the plain text comes out on the light board. So this was extremely sophisticated. It was used in World War II. But it turns out that at the time, having 3 rotors and a bunch of plug boards is actually enough complexity to hide the plain text. So you couldn't actually do cryptoanalytic attacks on anything protected by the Enigma. And it turns out that how the Allies ended up defeating the Enigma was that it was mainly like operational weaknesses. So things like the initial configuration of the plug board, as well as the rotors, that was all sent over plain text, and then they would use that to they would figure out how to like intercept the initial configurations, and then they somehow built their own Enigma, and then they inserted the configuration themselves, and they ended up decrypting it that way. Has anyone seen this CIA of information security before? It's a very common kind of like, what would you call these? These are like common ideas in like computer security, and that's basically information systems should have good availability, should have integrity. So by availability, that means anyone who needs to use the system should be able to use the system. Integrity means when you request information from the system, it's relatively you have a good idea that it hasn't changed, or like the data hasn't been messed with when you request it. And then confidentiality is that the information that you receive from the information system doesn't no one else can kind of like no one else can like, how would you say this, like spy on your interactions with the system. So cryptography is used in software to kind of achieve these 3 properties. In order to get confidentiality, we have encryption. which allows you, and also things like access control. So access control is certain users should be able to do certain things. Users who don't have certain permissions should not be able to do the things that you cannot do a privilege escalation without the proper permissions. And then integrity, that's done through hashing, which is, we'll go a bit more into it later, but hashing allows you to verify the integrity of a message. So if a message has been corrupted, then you cannot verify the original message without changing the hash. And then non-repudiation, which means I cannot pretend to be someone else without actually having that person's identity. So by identity in like the software sense, that would be like digital signatures. If digital signatures are created by a private key that only certain people are supposed to have, so you have your private key, I have my private key. Unless I have your private key, I cannot be you. And then privacy, which is not in this triangle, and to a lot of people that is actually not an important thing, but more and more we're starting to privacy is starting to become a more important topic to more people lately. We'll go more into privacy tomorrow because it's like a pretty weighty topic. Right. So hash functions, they're a basic cryptographic primitive that lets you map data of arbitrary size to data of fixed size. And so the idea of a hash function is that you can generate, when you compute the hash of something, it's relatively unique. So if you change the something, then the hash should be completely different. So it's one way of like fingerprinting data. If you change the data, then the hash should change. And then two completely different types of data should not produce the same hash, and that's called a collision. So basically what happens is, if you guys all remember back to the questionnaire, there was like that list of hash functions that had like the SHA-256 and SHA-512. What that stuff means is, so SHA-256 would output a 256 bit or like a 32 byte output based on any arbitrary sized input. So Claude Shannon talked about this like perfect secrecy thing. So if you don't, so what happens when you like map this arbitrary size into this fixed size space, you end up either losing a bunch of data or adding a bunch of excess data. So hash functions don't actually contain any, like you can't undo a hash function. That's one of the important things about this. It's not the same as encryption. Whereas encryption, you should be able to decrypt something that's encrypted. You cannot unhash something that's hashed. And it turns out that's a very powerful property because now you can use it for data integrity. What that means is like when you receive data, I mean, you guys have probably seen like checksums, like when you go to download files, they'll have this like hash of the file that you download. So after you download the file, you're supposed to hash the file and then compare the hash with the hash that's published. I don't know if anyone actually does that, but that's something that hash functions are used for. Yeah, and then so there are different types of hash functions. There's like MD5, there's a bunch of SHA families. And why there needs to be a bunch of different hash functions is because as people get better at math, as computers get faster, it turns out that certain types of hash functions do not really cut it anymore. So MD5, for example, is considered broken. You should not use MD5 for anything that's important. But it's still good for certain things, like checking the integrity of your files, for example. Hash tables, we'll talk about that a little bit later, but I mean, you're all familiar with hash tables. They're basically key value pairs or like dictionaries in Python. How you implement them, or how they're implemented in the backend, is they leverage hash functions very heavily. And that's, So here are some like attributes of a good hash function. So it should be deterministic. So that means whenever you should always it should always return the same output if you give it the same input. And that's if it doesn't have this property, then you cannot have message authentication, and that's because like if the message doesn't change, then the hash shouldn't change either. Hash functions should be reasonably should execute within a reasonable time. That actually depends on your use case. So for example, proof of work for Bitcoin, it's purposely done in a way so that it takes a considerable amount of time to calculate the output of your proof of work. And yes, irreversible. So like I said earlier, you shouldn't be able to undo a hash. That would be really bad. And then you're supposed to pick hash functions that have collisions appropriate with your use case. So if you're working in like a really tiny space with maybe only like 8 bits of data, then you could really use any hash function. But if you're trying to hash like gigabytes and gigabytes of data, I don't know why you would do that. But if that was the case, then like you probably don't want to use a super small hash function where the rate of collisions is super high, because then it's kind of like why are you even using a hash function? Yeah, so some hash functions, MD5, like I said earlier, has an output of 128 bits. Here's the link to the spec if you're interested at all. That goes through like how the function actually works and like the various things that happens inside of it. And like I said, it's broken. You can actually, I think there was a site where they had a bunch of pre-images of MD5, so yeah. I think in like the early 2000s, there were a bunch of websites that stored your passwords as MD5 hashes, which is like, now it's a terrible idea, but back then people used to do it. And like, there's the SHA family of hashes. So SHA stands for secure hash algorithm. I think we're on the 3rd family now. So yes. So SHA-3, I think there were a couple different algorithms for SHA-3. They're used a lot in blockchain nowadays. So Ethereum has SHA-3 primitives built in. There's an opcode to calculate the SHA-3 hash of something. Bitcoin uses SHA-3 for their proof of work. Yeah.
How can there be different algorithms for the same name? Like, why don't they just have different names for?
Yeah.
Because it's a little confusing, right? Like, you have to test which version of SHA-3 might be in a system that to find out if it's like CAC or something. Or
yeah. So SHA. The question was why SHA-3, or
like how can there be different algorithms for it? Why didn't they just decide to just have different names for each algorithm?
Yeah, so that's why so SHA-1, 2, and 3 stands for the generation of secure hash algorithms, and then every couple years or so they actually have this like competition.
Oh.
So CAC was the last name of the winning one of the contestants of the SHA-3 competition. And then the winner, I think their last name was CAC, so I'm not...
So SHA just refers to a generation of algorithms.
Yeah.
Oh, okay.
So there's SHA-1, SHA-2, and SHA-3. And then SHA-3, there were a couple... Yeah, so I forgot what the EIP was, but it was actually quite recent where Ethereum changed or not Ethereum. Was it Ethereum? It was either in the EVM or just for Solidity, where they used to use SHA-3, and then they had an EIP that changed it from SHA-3 to CAC, just to be more explicit because of like the problem that you mentioned. Yeah, so this is an example of how to calculate your SHA-3 hash. This is using Node.js, and the Web3 library. So Web3 is the Node.js library for talking to the Ethereum blockchain. Yeah. So you would use Web3 because Web3 has this solidity SHA-3 function. And this, if you use this, so Node is server-side JavaScript. Normally JavaScript runs in the browser. A bunch of people figured out that like maybe we should get the front-end developers to also develop the back-end, so they ported it over so that you can run JavaScript for your back-end. And this is useful because a lot of people use browsers. So you want your browser to you want people to use your blockchain. So it's in your best interest to make sure that whatever happens in the browser matches whatever happens in the blockchain. So the Web3 library has this built-in solidity SHA-3 function. And if you use this, it actually calculates the SHA-3 hash exactly the same as how it's done in the EVM. So if you were to do things where you need to hash something and then compare it to something in a smart contract, you should make sure that you use this function. So yeah, so if you count, I think this is 32. It should be 32. So if you count this, there should be 64 characters, and then you see that my input was significantly less than 256 bits, but the output is always this big. And then there's also a Web3 library for Python. So if you prefer Python over Node.js, you can pip install Web3. And then this Web3 also has a SHA-3. So you see I entered the same input and then I got the same hash here. So A3E82. This is also A3E82. And then you can also calculate the same hash in a solidity. Oh yeah, so this is the EIP I was talking about, where they asked to change the name from SHA-3 to KCAC 256, and then I think they're actually aliases now, so on the EVM they're the same opcodes. Yeah, so these hashes exactly the same as in Python and Node.js. Any questions so far about hash functions? Okay. Yeah, so let's go through a use case for hash functions. So there's this idea called a commit reveal voting, and we're actually going to build this out next week as a in-class assignment. It's pretty simple. So the idea of this is how do you create So the reason behind commit reveal voting is how do you get people to vote during a certain period without revealing everyone's votes? So that's useful for a lot of things. So I'm drawing a blank, but let's say like elections, right? So you want to vote for your favorite candidate. It's probably in everyone's best interest for the voters not to see the results in real time as the votes come in, because then you'll have this, what would you call it, like voter bias, where maybe if one person's winning, you'll think, oh, my vote doesn't really matter. I'll just put it into whoever's winning. And then you end up having these like not fair votes where the voter is influenced by the results of the vote, which is not good because the voting hasn't ended. So what happens in the commit reveal voting is everyone generates a secret that they use during the voting phase. So this smart contract implements sort of like a state machine. So the first state would be the voting phase, where everyone just submits their vote, and everyone submits their vote as the hash of a secret value that they generated, as well as their actual vote. And then they submit this hash onto the smart contract. Since everyone generates their own secret and no one knows anybody else's secret, they cannot figure out the vote. Everyone with me so far? Okay. And then in the second phase, which is the reveal phase, you send the secret that you used for the voting phase as well as your vote. And then in the smart contract, it hashes the secret and the vote in the same way that you hashed it when you submitted your vote, just to verify that you didn't change your mind or you didn't, just to make sure that you didn't change your mind and your vote was valid. So if this hash that the smart contract calculates matches the hash that you submitted during the voting phase, then your vote is counted and like is tallied and so forth. Make sense?
And so the way to break that would be to try and find a different secret when combined with the vote that hashes to the same value. That would be how you break it.
That's one way of breaking it. But the idea, ideally,
change your vote.
Yeah. Ideally, you make everyone pick really big secrets so that it becomes like impossible to brute force. That, and you pick a really large hash function just to make it so that it's not realistic to break. So yeah. Any questions about this?
Not really a question, it's more of a clarification. So if the age of S1 comma vote is basically a concatenation of S1 and vote, right?
Mm-hmm. And then you hash the concatenation.
Because like most of the time the SHA takes this single argument and like multiple arguments.
Yeah, no, you would just like concatenate them.
Okay.
Yeah. Because the input to a hash function can be arbitrarily sized.
But this one is not anonymous. It's just a way to make sure you don't change your mind.
Yeah, exactly. So it's the main. It's not anonymous because of if this was on Ethereum, you'll need your public address to submit the vote to interact with smart contract. And so what this does is basically it hides everyone's votes until the reveal period.
Okay.
And because everyone kind of agrees how hash functions work, they trust that like during the reveal period when they tally up the votes that everyone that it was actually correct when they add it all up.
So it means that in order to count all of the votes, all of the people that participated in the commit phase, they all need to do this all over.
Yeah, so it's a very interactive process,
Okay.
which you'll find out really quick that users really hate doing things, and the more you tell your users to do, the less likely that they'll do it. So it's definitely not a really good like this probably wouldn't work really well if you wanted to like run an election this way, because people already don't show up at the polls. Now you're telling them to show up twice. It's probably not going to work. But it's a good exercise for like hash functions and just smart contracts in general. And then digital signatures are another cryptographic primitive. They're analogous to traditional signatures. So you think back to when you need to sign something and why you need to sign something, and that's to prove your identity. Even though like people suck at signatures, and I'm pretty sure no one actually does their signature exactly the same more than once, but it's a very like traditional way of authenticating something and signing off on something. So the idea of a digital signature is that you have a private key and a public key. The private key you keep private to yourself that you use to generate the signatures, and then the public key can be used by any third party to validate your signature. If anyone like follows blockchain news, Estonia do you have an Estonian? Yeah, right on. Yeah, so you can sign up for to become an e-resident of Estonia, which is extremely exciting because they ship you this little card, and they ship you a reader for the card too. I think it's a smart card. It looks like those credit card chips. Yeah. And then the idea is that your private key is on the card, so now you can generate signatures. And I think they actually use this to like sign contracts and documents now. And yeah, I think it's like $100 or something. It's not ridiculously expensive.
I paid €100 for it.
Yeah.
actually. Yes.
And you can use lots of places.
Just in Estonia, but you can run a company in Estonia. Is that?
Yeah, because like
when you run your
Estonia is part of the EU, so now you can actually like do business with European.
Okay, I have a company, the TVA.
Could you get an EU bank account?
Yeah, you can open a bank account. Yeah, it's very convenient.
That's neat.
Yeah, and then the specific digital signature algorithm is the ECDSA, so that's the elliptic curve digital signature algorithm. It's we're not going to go into what elliptic curves are because it's kind of hand wavy, but the idea is that you so these are Bitcoin private keys and Bitcoin public keys. They look like this. And then Ethereum is slightly different, but they're all the same thing. It's just that Bitcoin uses a different type of encoding and then Ethereum uses another type of encoding. So that's why they end up differently. They end up looking differently. But as developers, you're really only concerned with two functions when you're interacting with digital signatures, and that's the sign function to sign some data, and then verify, which is to verify that the data was signed by whoever signed the data. And there's these three variables, V, R, and S, and they are used like this. I thought I had code here. There's no code. Maybe it's the link. Yeah. Has anyone used MetaMask before? Or actually, I think Ali probably used MetaMask on the other day. Yeah, so MetaMask actually lets you... So MetaMask, basically, it's your wallet in the browser, and it stores your private key, your Ethereum private key, in the browser. And you can actually prompt your users to... If you make a web app, you can prompt your users to sign messages through MetaMask. So this is what comes up. And then on your back end, it looks something like this. Where is it? Oh, no, this entire thing is the function. Oops. Yeah, so function sign message, and then you call sign message from anywhere, and it should prompt your user with that screen as long as they have MetaMask installed. If you guys do end up using MetaMask, you should note that they changed it recently, so you actually have to prompt your user to allow you to interact with MetaMask before you can interact with MetaMask, and that's because... Where did it? Yeah, so this web3.eth.getAccounts. Oh yeah, so if your user has MetaMask installed, so that's like this. Oops. Yeah, so, oh, why is this happening? Yeah, so I don't know if you can see this. Yeah, if your user has the MetaMask plugin installed, the plugin or the extension injects the Web3 library into their browser. So then, yeah. And yeah, so that's why if I type Web3 into my browser console, you actually get something. If you use, do I have it in? So if MetaMask is not installed, then Web3 doesn't do anything. But yes, I don't think this web3.getAccounts works anymore. Oh, it does. Do this. thought this wasn't supposed to work. Oh, yeah, okay. So accounts is empty. And that's because MetaMask updated recently. Oh, what's happening? Okay. Did everyone do this with Ali the other day?
Yeah.
Everyone made their MetaMask. Yeah, so I found out recently that these seed phrases, they're not random words. There's actually a word list for seed phrases, and it's all there. Oh, wait, why is it working? It's supposed to prompt me. Yeah, so you notice how there's nothing here, and that's because your user actually needs to unlock their MetaMask. Does it work after the unlock? Yeah, it still doesn't work after the unlock. Maybe Brave behaves differently, but there was yeah. So you notice how as soon as I ran this, it gave me my public key. The MetaMask did an update recently. I don't know if it works on Chrome. Maybe it was, or if it works on Brave, it might just be Chrome. But basically, they're trying to stop websites from. So there were these sites that were just kind of collecting people's public keys, because as soon as, if you have MetaMask unlocked and you ended up on their site, they can just have like. They can just harvest your public keys, and turns out that is not a very good thing, because if you have people's public keys, you can I'm sure you've all done this before, but you can like go to Etherscan, and then you can look at this guy with this address, and you'll be like, whoa, they have so much money. Or I guess this guy doesn't have that much money, but yeah. So it's like, sure, you don't know who they are, but if you know their spending habits and they make enough on-chain transactions, you might be able to deduce like who they are, and then that's not extremely safe, especially if you are a important person, or yes. So yeah, you can use Node.js, or not Node.js, JavaScript on the browser side or on the client side to prompt your users to sign messages through MetaMask. So that's a very common way of doing it. A lot of decentralized exchanges do it that way. So when you go into a decentralized, actually, yeah, let me show you. So Fordex is a decentralized exchange. I think Ali talked about 0x the other day. So Fordex is a relayer on top of 0x, and they use MetaMask as their identification system. So now instead of having like username and password, you sign in with MetaMask. Yeah, so this is the thing that's supposed to pop up and ask you who you are, or ask you for permission to allow the app to connect to you. So I say connect, and then suddenly everything works. So yeah, that's a nice thing about this is that I don't need to remember my username and password. I just need to be able to unlock my MetaMask. And then this became my identifying thing, my identification. And then you can do a similar thing with Python. Which was this again? Yeah, so this Python would be server-side because I don't think you can run Python on the browser for your clients. But yes, this is how you would sign using Python. So you call you import Web3, and then you call the sign hash with your message or your message hash, and then the private key to sign it with. And then it'll generate these three parameters, R, S, and V, and then the actual signature. Yeah, so you never really want your smart contracts to generate signatures because your smart contract doesn't have a private key, and you also don't want to store user private keys on a smart contract because then that means everyone else can see the user's private key, which is not really good. So what you do on the smart contract is you use it to verify signatures. So this is how you would do it in Solidity. Very quickly, what Solidity looks like. So there's this pragma line which tells you what version of the compiler to use. So if you put this little caret thing, it means use anything greater than 0.4. And then Solidity, you can think of contracts as if they're objects-ish, kind of. And how you define that is with this contract keyword. And then, so this is your contract, and then your contract has functions. So this is the check signature function. And to validate signatures, you need the message that you're checking the signature on, and the three variables R, S, and V. And if you remember from back here, when you generated the signature, it spat out these three R, S, and V variables. So these are the three variables that you use to verify the signature.
I heard there was some kind of bug originally with the V, and because V needs to be 27 or 28 or something, and that was because of some bug. Do you know anything about that?
I don't. It sounds kind of familiar, but I don't remember the details for that. Sorry. Any questions about signatures? Yeah, and then the last cryptographic primitive that we'll go over is encryption. So encryption, very similar to the classic examples I gave in the beginning, is it's something that you use to hide data for retrieval later on. And there's mainly two types of encryption. There's symmetric encryption, which means you use the same key to encrypt and decrypt. And then there's asymmetric encryption, which is where you use a different key for encryption and another key for decryption. And it's important to know that there are no encryption primitives built into the EVM and therefore into Solidity. If you try to roll your own, you probably can't because there's a gas limit. We'll go into more details what that means in the next couple days. But overall, you probably won't be able to do any sort of encryption on your Ethereum smart contracts. Yeah, so symmetric encryption is pretty basic. You use the same key to encrypt and the same key to decrypt. So here's an example for asymmetric encryption. So you have Alice here, and she has private keys SKA and public key PKA, and then Bob has the same thing. So if Alice wanted to send a message to Bob, she would use Bob's public key to encrypt the message. So sending message M1 using public key of Bob. So anyone in the middle who reads the message, they won't be able to decrypt it because they don't have the decryption key. So the decryption key is Bob's private key, and he uses that to decrypt the message. So the public key is available to everyone, and then the private key is something that you keep private. Asymmetric encryption makes sense. And then there's this homomorphic encryption, which is sort of like, it's a really active area of research right now. So the idea of homomorphic encryption is that you can encrypt data, but after you encrypt the data, it's still, you can still do operations on the data. And then you can decrypt the results, and it will be as if you did the operations on the plain text. So this means, this is like a huge privacy thing where, say you had a bunch of patient data, and then you wanted someone somewhere to do math on the patient data, but you don't want them to know who the patients are, or you don't want them to know what the data actually is. So you will send them this homomorphically encrypted stuff, and they'll do a bunch of operations on it. They have no idea what they're doing, obviously, because it's homomorphically encrypted, but they'll send you back the encrypted results, in which case you decrypt it, and it'll be as if they did the operations on the unencrypted data. So this is a very, so there's homomorphic encryption, and then there's fully homomorphic encryption, which is what I just described. Fully homomorphic encryption doesn't really exist. There are a bunch of people there's a bunch of research happening in this area. This episode 60 of Zero Knowledge, it's a podcast, and this episode they talk about, I think it was with New Cipher, but basically they explain homomorphic encryption a lot better than I did, and it's worth a listening to. It's worth a listen if you're interested at all. So check this one out. Yeah, there's something. Has anyone ever heard of vanity addresses? No. So you notice how so this is a Bitcoin address. It starts with 3. All Bitcoin addresses start with 1 or 3, so that's nothing special. But the next 4 letters are BMEX. And then later you'll find out that this is actually BitMEX's account. And that's because you can keep generating addresses until you get certain letters. And then these are called vanity addresses, and they're worth a lot. So there's actually, there was I think it was this one. Yeah, it's this one. So this is a service where you can, they can create Bitcoin addresses for you, which if you think about it is kind of weird, because in order to generate an address they have to know your private key. So it's wait, but yeah, so up to 6 characters you can get it for free. So if I wanted David, yeah. Oh, yes. Did they have an about? They don't. But yeah, supposedly they're supposed to be using homomorphic encryption to generate the addresses. And then when you, after they generate your address, they don't know your private key, and supposedly only you can get your private key after you decrypt the payload that they send back to you. So, and that works because the ECDSA key pairs have homomorphic properties, and both Bitcoin and Ethereum public-private keys are ECDSA public-private keys. So, but they're just encoded differently, so that's why they look different. But in the backend, they're both for ECDSA, and that's why you can do things like sign transactions and verify transactions and so forth. And I think there was some talk about numeri in the Slack channel. Did Ali talk about that, or was that just something that
I had a few questions for him about it, and he chatted a little bit about Ethereum too.
I see. Yeah, so numeri is very interesting. They're supposed to be using homomorphic encryption. There aren't that many details about what they actually do or how they do it, but it seems like people are using it, and I think the founder of numeri was actually on Zero Knowledge. They interviewed him, and it sounded like they were doing pretty well. So I think it works. Yeah. Right, so there's a assignment that's due in 2 weeks, and this is it's assignment that kind of introduces you to all the cryptographic primitives that we talked about today. It's pretty interesting. You're basically making a bank in Node.js, and yes, so on this slide there are some links. Is there anyone that has never worked with JavaScript or Node.js before? You'll be okay. So, yeah. You're running Windows, or?
I can. But yes.
Yeah. Well, it's I always found Windows kind of finicky. So like if you have like Ubuntu or Linux installed, then like it's way better.
Okay.
Yeah. So follow this link, and then especially if you're using Ubuntu, make sure you do this fix these npm permissions, or else you can't really install things, and that kind of sucks. Yeah. So
in terms of submission, can we just like send you a link to a Git repo?
Yeah, for sure. So like, yeah, feel free, like either zip it up and email it to me, or like create a Git repo and then send me the link. Yeah. So it's a pretty straightforward assignment. On the link, there's a bunch of readmes or markdown files, and then you just read them. They basically walk you through what to do. Yeah, so I'll do the first couple questions with you guys, because they're basic and like nothing is really happening. So this first one is you create a banking server and a teller client. So if you're not familiar with how banks work, there's the bank, and then there's a teller who is an employee of the bank, and they are the person that you interact with. So in this case, the bank is the server, and then the bank teller is the client. Banking server represents the bank vault, the bank is the teller used to deposit and withdraw funds. Right. So here's like some example code, server, client, and what we'll do is I hope I have Node installed.
Can you make your text bigger?
Yeah, one second. So I will follow this. They want one file called bank.js. And you basically, oh no, that's not good. So I just copied the code from the markdown file, and yeah, so this is a bank. It just pretty simple. Imports some libraries. Yeah, so it imports the duplex JSON stream library, the .NET library, and then creates a simple Node.js server. And this server opens a server on this port and then basically just echoes. So console.log is like print to the console. It logs to the console whatever is received on the socket. And then there is the teller file. This is the client side. It connects to the same port as the server and then sends it a piece of data and then read something. So how you run this is, I think I have Node installed. So you node bank.js, and that basically runs the, oh, I don't have Node. Oh, yes. There are some dependencies. So if you go back to, oops. Do they have the dependencies here? They don't. That's not good. Yeah, so as you run through the assignment, you will probably notice that you're missing some packages, in which case you will do npm install, and that's the node package manager, and you install whatever they say is missing. So here, I just installed that duplex thing, and I'll try to run it again. Does it work? Oh, what is this? Oh, can't be that bad. I think it's running. And then you open up another window. Oh, okay. So here's like, that was the basic code that they gave you, and then the problem for the first problem is to extend the client to send command balance. So this is a command that the client sends to the server, and then have the bank reply with command balance 0. So it's supposed to, the bank is supposed to echo the command and then give it the results of the command. So let's go to the teller, and how does this work? So this duplex JSON stream, if you Google it, you'll end up at their Git repo, in which case you go down to the usage and they'll teach you how to use it. It's amazing. They're very nice people. And it turns out that you can directly write to these sockets. Are they really sockets? I guess they're sockets. Right. So here the client has been connected. Let's try client.write. Well, what did they want us to write? Command balance. Is that it? Can you do that? I feel like it should be a string. Maybe it doesn't need to be a string. Oh, looks like oh no, it doesn't work. Oh, the server is not running. Yay. So, yeah. Client, you create a client, which is a JSON stream connected to this port. And supposedly this port you're running on in another console, you're running a server on the same port. So here is that server that you created earlier, and then you instruct the server to listen to this port. So now I have the bank running here, and then on the client side I'm writing this raw JSON object to the client, and the client is connected to the port that the server is listening on. So I just do client.write JSON object and run the client, and then on the server it says I received it. So how do I, what was the other part of the question? The other part of the question was that the bank has to reply with this response, which is nothing, I guess, but we will do that. So let's edit the bank, and then, oh, there are instructions here. Okay. So on the bank, let's just blindly reply with the balance whenever we receive something. So this socket.on is like a callback, I think. You're registering a callback to whenever data is received. And whenever data is received on the server side, you'll log whatever you received, or you'll print whatever you received to the console, and then send back the balance of the account to the teller. So if you run the bank again, and then you run the client, you'll see that the client sent something to the bank received it, and then sent something back. And then on the client, you'll see that we received this thing, which is what the bank sent it. And then now we're done question 1. Any questions? Quite simple. Very good. Let's move on to question 2.
So was the like crypto portion of that?
There was no crypto in that. Yeah. Is there crypto in this one? There's also no crypto in this one. It's not good. Where is their crypto? There's no crypto here either. Yeah, so there's no crypto until question 6, which is fine because all the other ones are leading up to question 6. So what the assignment asks you, or the assignment instructs you to use the sodium library, which is perfectly fine. You can use it. But if you're feeling adventurous, I encourage you to use the Web3 library that was in the slides. And that is, yes. So when you're using the Web3 library, basically all you have are, you have hash functions and you have signatures, but you don't have encryption primitives built into Web3. So when the last couple problems require you to encrypt like the bank balances for obvious reasons, and for like teaching you how to do encryption. For those ones, you have to use Sodium. So this is a Sodium native. Sodium native, you need it if you do a Sodium native is for Node.js because it runs on your actual like machine. There is another one, I forgot what it was called. I think it was Sodium Web or just Sodium. That's what you need to use if you ever decide to do this in the browser, because Sodium native doesn't work client side because it's for native usage. So yeah, keep that in mind if you ever decide to do it on the browser. Yeah, other than that, is there anything anyone wants to discuss, talk about, questions, ideas?
I have a general question. So for like developing decentralized apps, like since you're in the space, which one's the most popular? Is it the Python, is it the Node, or is it like Solidity?
You kind of need both. So Solidity is, we'll go into more details next week, but Solidity is a library, or is a language built on top of, Solidity compiles into bytecode for the EVM, and then that bytecode gets executed by nodes, by Ethereum nodes, or full nodes more specifically. Yeah, so if you want to write smart contracts that get deployed onto Ethereum, you have to write Solidity. I mean, you don't have to write Solidity. There's also Viper. You can write raw bytecode if you really want to. Don't laugh, because like people do that, you know.
Well.
No, you actually have to do it because of gas limits. So there's actually, we'll talk more about gas limits. If you just do Solidity, sometimes it's not the most optimized, so you'll have to drop into assembly. Like you can do inline assembly in Solidity just to like optimize some of your functions. Yeah, because this gets to the point where like optimizing actually pays off, because now like your users don't have to pay as much gas. There's a lot of discussion right now, especially with like Ethereum 2.0 like rolling in slowly, to like figure out ways to offload the gas to the developers and not to the users, because it really sucks for a user. Like first of all, I don't really know what a smart contract is, and then I don't really know what a decentralized app is, but now I'm using this thing and I have to pay for it. Like that's terrible. So yeah, there are a bunch of ideas about like how to shift the cost of gas, and we'll talk about next week why gas is even necessary. And it turns out like it's a really important concept, especially for Ethereum. But yeah, back to your question. If you want to write smart contracts, there are a lot of platforms. A lot of them are based off of Ethereum. So what they end up doing is they build their own blockchain, they have their own nodes, they develop their own network, and then they fork the EVM. So they take whoever's implementation of EVM. There are a bunch of implementations, but basically they have their own blockchain and all the nodes run a version of the EVM. And since they're running the EVM, anyone can write smart contracts that usually work on Ethereum, but now you can just run it on these other blockchains. Some prime examples are Tron. Tron can run smart contracts originally for Ethereum, but now it's on Tron. What was the other one? Skipped my mind. Well, Hyperledger Burrow is also a fork of the EVM. JP Morgan's Quorum, which is like, is basically Geth. They forked Geth a while ago. Geth is Ethereum client written in Golang. It's one of the more popular Ethereum clients right now. Quorum is basically Geth from like a while ago. They forked it, put a JP Morgan logo on it. Now it's a corporate blockchain. Yes. So EVM is probably one of the main smart contract engines out there. There is Neo, like the Chinese Ethereum. Neo has their own virtual machine that runs their own type of smart contracts. Those smart contracts are written in, I think it was C#. I don't remember. But it's another language that can compile into bytecode for their smart contract. Yes.
Do you remember Tendermint and Cosmos?
Yeah, those ones. I think Tendermint runs EVM, but their consensus and everything's like different and supposedly better. I haven't dug too deep into them, but yeah, those are alternatives. So yes. And then the Web3 stuff, speaking specifically to Ethereum, Web3.js, so the JavaScript library is more popular than the Python one. They both work last time I checked. I've used both of them a while ago. And yeah, so that is something that you would use, like the JavaScript library and the Python library, you would use those client side. So for example, if you wanted to say scan the entire blockchain and find out, if you wanted to like scan the blockchain, you would use one of those libraries. So you can write your scripts in Python or in Node and then connect to an Ethereum node and use that library to like parse transactions, parse blocks, whatever. Yeah. Did that answer your question?
Sure.
Yeah. There's also this remix. We'll go in. Sorry?
It's like an idea or something.
Yeah, we'll go into more details next week, but then it's a very, it looks really like simple, but it's actually pretty complete. And it's basically somewhere, it's a browser. So they put a Solidity compiler in the browser, and yeah, so you can write your Solidity smart contracts and then you can compile them all in the browser. You can even deploy them to the blockchain from the browser. And can I do that? Probably can.
It's kind of broken in Firefox right now.
Oh no.
But works well on Chrome.
I'm on the mainnet. Yeah, so you can actually deploy to the blockchain from Remix because it connects to MetaMask. So yeah, so say I write my smart contract and then I hit compile, I can actually go to run, and then here this environment. This environment selects where, like how you connect to the blockchain. And injected Web3 is MetaMask. JavaScript VM, it tells you what it is. Oh yeah, so JavaScript VM would be like running, it's actually pretty crazy because it runs like a simulated version of Ethereum in your own browser, but it's just you, so it's kind of boring. But it works really good if you want to like test out how your smart contracts are working. Yeah, so if you hit deploy, it actually prompts MetaMask to pop up. And then MetaMask comes up. And then you can see it costs you gas to deploy smart contracts. And we'll go into more details about that next week. Stay tuned. yeah, this is worth a look at. It also has this really cool thing. I hope they still have it. Yeah, it has dark mode, so you can go to dark theme. Yeah, check that out. Now it's dark.
Dope.
Yeah, it's pretty great. It also has a debugger, which is crazy because now you can like check. Wait, can you do blocks like that? Oh, maybe you can't. Oh, you can. Wow. Why is it all empty? Oh, you have to actually have the smart contract. But yeah, you can actually peep into the stack or the storage or the memory of your smart contracts. Yeah, it's pretty crazy for like a web IDE. Yeah, so let's work on the assignment for the rest of the day, and then I'll be around to answer any questions